Certainly. Here's the punctuated version of your text. In the gigantic universe, where mysteries multiply and the real surface of spacetime is stretched out beyond what many would consider possible, a huge mystery has emerged. How we could decipher the advancement of the universe is at an intersection with new verification, testing well-established speculations, and suggesting hidden-away powers that could reshape the genuine foundations of cosmology. This obliges us on a journey through the latest disclosures and significant jumps into the secrets of the universe as we research the enchanting and debatable question. How quick is the universe genuinely developing? Something is off with how we could decipher the universe. Cosmology is apparently making a beeline for a standoff over maybe its most focal question. How quick is the universe growing? For more than 10 years, two sets of measures have been in battle. Impressions of the universe today for the most part show that the speed of extension, known as the Hubble constant, is around 9% faster than assumptions. In view of information from the early universe, experts trust the James Webb Space Telescope, the most advanced telescope ever developed, would help with settling the question unequivocally. Yet, as of now, no arrangement has been shown up at. Rather, the Space Observatory has developed the uniqueness with incredibly careful, notable insights that did whatever it takes to bring down the standard model of cosmology. The new physics expected to reevaluate or even replace this 40-year-old speculation is now the topic of conversation. One captivating and enchanting possibility is that there is something we don't understand about the universe. This obliges us as we examine the new, truly significant pictures from James Webb that have recently affirmed that there is something truly amiss with how we could decipher the universe. Our universe started with an impact, the enormous detonation. Energy, mass, and space showed up in a passing second. Then, the young universe framed a sputtering, developing plasma of matter and antimatter particles that appeared to annihilate each other on contact. Left to their own devices, the matter and antimatter inside this plasma should have annihilated one another. Yet, researchers accept that a dark disproportion allowed more matter than antimatter to be made, thus saving the plasma universe from quick collapse. Gravity squeezed pockets of plasma, compacting and warming the material so that sound waves, going at around a portion of the speed of light, called baryonic acoustic oscillations, undulated across their surfaces. Meanwhile, the high energy density of the early universe and its muddled objects grew at spacetime, pulling a little piece of that out of the contention. As the universe expanded like an inflatable, the normal story goes that normal matter, associating with light, joined around imperceptible lots of dark matter to shape the primary universes, connected together by a colossal, vast web. From the start, as the objects in the universe extended, its energy density and thus its speed of development lessened. Anyway, around 5 billion years ago, the universe started to advance at a constantly expanding rate. The explanation was a new, undetectable, and bewildering component considered dark energy. The easiest and most notable clarification of dark energy is that a cosmological constant, an inflationary energy, is the same everywhere and consistently woven into the texture of spacetime. Einstein named it lambda in his general theory of relativity. As our universe has extended, its general matter density has lessened while the dark energy density has continued as before, consistently making dark energy the biggest supporter of its general extension. Taken together, the energy densities of standard matter, dark energy, and light energy set a furthest breaking point on the speed of the universe's extension. They are additionally key parts in the cosmological lambda cold dark matter model, lambda CDM, which guides the universe's turn of events and predicts its end, with issue at last extending until it will experience a stage known as the enormous freeze. Some of the model's forecasts have demonstrated shockingly exact. Anyway, this is where the issues start. Regardless of much exploration, cosmologists still don't know what dark matter or dark energy is. As Ofer Lahav, professor of cosmology at University College London, who concentrates on dark energy and worlds, puts it, by far most concur that the ongoing construction of the universe is 5% conventional baryonic matter, 25% cold dark matter, and 70% dark energy. The humiliating truth is that we don't comprehend the latter. An excessively large danger to the lambda CDM model has emerged. Depending on the method astrophysicists use, the universe shows up to extend at various rates, a disparity known as the Hubble tension. Preliminaries of the early universe show that it was extending a lot quicker than lambda CDM expected. These strategies have been checked and affirmed by various perceptions. As astrophysicist Adam Rees, Nobel laureate and head of the team that made James Webb's new estimation, said, "The main clarification I can see right now for why they vary is that the model we have between them might be missing something. Estimating the extension of the universe requires more than just radar." The essential strategy to measure this development took a gander at the purported cosmic microwave background, CMB, a remnant of the principal light known to humankind, made only 380,000 years after the Big Bang. This leftover is noticeable all around the sky, and it was mapped by the European Space Agency's Planck satellite to track down the Hubble constant with an error of under 1%. From 2009 to 2013, in the Planck picture, the universe is totally homogeneous. However, the warmer and colder areas where matter is more or less dense reveal places where the baryonic acoustic vibrations have caused it to group together. As the universe extended outward, this web structure developed into a grandiose web, a multifaceted organization of fibers along the convergences of galaxies. By examining these waves with the Planck satellite, cosmologists have finished up the sums of normal and dark matter, too, as the value of the cosmological constant or dark energy. Consolidating these into the standard model gives a Hubble constant of around 67 kilometers per second per megaparsec. How about we center around that number briefly? If a galaxy is 1 megaparsec away from us, that means it is retreating from us and we from it at a speed of 67 kilometers per second. At 20 megaparsecs, this pace of downturn comes to 1,340 kilometers per second and keeps on expanding. On the off chance that a galaxy is more than 4,175 megaparsecs away, it is retreating from us quicker than the speed of light. A second strategy for tracking down this development rate utilizes throbbing stars called Cepheid variables, dying stars whose external layers of helium grow and contract as they ingest and produce radiation, making them occasionally flicker like far-off beacons. In 1912, astronomer Henrietta Swan Leavitt found that the more brilliant a Cepheid star, the more slowly it flickers, permitting space experts to measure a star's absolute brightness and consequently gauge its distance. It was a milestone discovery that made Cepheid variables the omnipresent standard candles for estimating the immense size of the universe. By joining discoveries from perceptions of Cepheids, cosmologists can assemble estimations of immense distances, with each step taking them further back in time. It is maybe the most dependable technique stargazers use today to gauge distances and construct a vast distance stepping stool. Cosmologists first form the stepping stool by selecting close by Cepheids and estimating their distances against light. Wendy Friedman, an astrophysicist at the University of Chicago, made sense of that, ensuing advances utilized just Cepheid variables. Next, cosmologists checked out the distances of the stars and supernovae on each bar and thought about the degree of the redshift of their light, which shifts toward longer red frequencies as the universe extends. This took into account an accurate estimation of the Hubble constant. In 2019, ongoing teams utilized this technique to focus on the Hubble Space Telescope at one of the local group's closest neighbors, the Large Magellanic Cloud. Their outcomes were strikingly high, showing an extension pace of 74 kilometers per second per megaparsec, contrasted with Planck's estimation. Anyway, Hubble missed the mark on accuracy expected for the messy regions of space the team was concentrating on, causing a portion of the far-off Cepheids to mix with neighboring stars. Critics have contended that this shocking outcome could have come from an estimation blunder. So, when James Webb launched in December 2021, it was ready to either resolve this disparity or affirm it. At 6.5 meters wide, Webb's mirror is almost multiple times bigger than Hubble's, which is just 2.4 meters wide. Moreover, James Webb can distinguish objects almost multiple times fainter than Hubble and is likewise undeniably more sensitive in the infrared range, permitting it to see across a more extensive range of frequencies. By looking at the Cepheid variables measured by James Webb and the galaxy NGC 4258 with bright Type 1 supernovae, another sort of standard candle since they all detonate with the same absolute brightness, Rees and his partners delivered a practically indistinguishable result, 73 kilometers per second per megaparsec. Other estimations, including one made by Friedman with the Hubble Space Telescope of the quick lighting up of the red supergiant branch and another of light bent by gravity from enormous galaxies, returned values of 69.6 and 66.6 kilometers per second per megaparsec. respectively. Another result utilizing light bending likewise gave a value of 73 kilometers per second per megaparsec. Cosmologists were astounded by these results. Rongzhen Chang, a cosmologist at the University of California, Merced, who worked on the Hubble constant. Results says, there was an energy of sorts around this worth. It is fascinating to consider. The mystery of these results is that they are generally conflicting with the lambda CDM model, the dominant cosmological model of our universe. It is still early days in the cosmic exploration venture. It is conceivable that the new physics could reveal another cosmological hypothesis, reshaping how we consider our universe. While the standard lambda CDM model portrays a universe that has expanded at various rates since the huge blast, the new physics could disclose a more multifaceted history for the universe. The issue with the present cosmology is that the lambda CDM model depicts the extension of the universe as steady and unsurprising, a story where the rates of the universe's extension are uniform. Alternatively, dark energy models are evolving into versions with a variable extension rate, showing that there is more to consider about the extension than meets the eye. New pictures of this development could show that there are fundamental issues at play. In the meantime, cosmologists will keep on concentrating on these mysteries. They are striving to be certain of the new proof. As Adam Rees said, we are quite a bit nearer to answering the inquiry of how quick the universe is extending. As cosmologists refine their measurements and figure out how to get the universe, the answers will be revealed. With more observations and better information, they will solve this cosmic puzzle. The science of how fast our universe is developing might shape the future of cosmology and answer fundamental questions about our universe.